KNIT Sultanpur in year 2002 and the MTech in Electrical Engineering from IIT Kanpur in 2004. Sir also completed his PhD in Electrical Engineering from IIT Kanpur in year 2007. He is the recipient of Cadence Gold Medal in MTech. After PhD, he worked with General Electric Global Research Center, Bangalore. Presently, Sir is professor in Department of Electrical Engineering, IIT Kanpur, from January 2009 to till now. He has authored more than 240 journals and conference papers with international repute. Also, he has supervised 41 MTech theses and 7 PhD theses till now, and also currently involved in it. He is involved with several research projects with DST, ISRO, DRDO, MHRD, etc. Sir has received Young Fellow Award from IIT Kanpur. So, with this introduction, let me call Professor Kumar Vaibhav Srivastav to proceed over the session. Welcome, sir.
Thank you, Manisha. Thanks for nice introduction.
Thank you so much, sir.
If you can stop sharing, then that I will start. And yeah, thank you.
Sir. I would like to welcome Professor Ramapati Mishra, sir, Director IET, here on this platform. Good morning, sir.
Very good morning, madam, and Professor Kumar Vaibhav, sir.
Good morning, sir.
सर अभी तक मैं म्यूटेड था.
Sorry, sir, मैंने ध्यान देखा नहीं actually.
इसलिए I could not pay due salutations to Speaker Professor Vaibhav Srivastava, sir. I welcome you, Your Honor. And मैं सर आपकी IIT की लैब में गया था, अगर आपको याद होगा.
Yes, I remember, sir.
मैं सर यहाँ पर मैं 5G का कुछ इंस्टॉलेशन के चक्कर में आपसे मिला था, सर. I welcome you and salute you, sir, for giving us time, sir. My student will be really benefited by this.
Thank you, sir. Thank you.
Over to you, sir.
Okay. So, can you share? Can you see my screen?
Yes, sir.
Okay. So, this one is like that the RF and microwave characterization laboratory. So, objective here is like that if you find like many engineering college that the people are not very much encouraged to go in this area, or sometimes that the people or the student find difficulty in understanding the concept of RF, microwave, or electromagnetics. So this lab is actually planned to. I was just trying to. Yeah. So this lab is actually planned to understand the concept of that the RF and microwave. So whenever we actually go from that the low frequency to that the high frequency, the concept actually becomes changing over there. Like instead of that the talking the term of that the voltage and current, we actually talk about that the electric field and then the magnetic field. And if you'll see like the most of the communication system, that is all happening at the microwave frequency. I don't know, someone is actually using that the.
Sir, one thing. आप अपने स्क्रीन पर जा करके जो व्यू ऑप्शंस हैं उस पे जाएंगे तो वहां से आप डिसेबल कर सकते हैं सबको.
एनोट करके एक होगा सर, उसको डिसेबल कर दीजिए.
एनोटेशन बाय अटेंडीज सर.
एनोट
हाँ, ये आप जब व्यू पर जाएंगे सर.
यस सो आई हैव टू गो टू एनोट.
यस सर. ये परितोष
रमेश
सर, व्यू ऑप्शन पे सर आपको जाना है. उसके बाद आएगा ऑप्शन एनोटेट. एनोटेट पे आप गए और उसके बाद आपको वहां से डिसेबल कर देना है फॉर अदर यूजर्स लिखा होगा समथिंग इस तरह का.
Nothing. It shows all those annotate option, but
नहीं, annotate है. Your Honor,
annotate पे आपको जाना है सर और क्लिक करना है.
7th पॉप डाउन है, 8th 9th
डिसेबल करना होगा सर. नीचे जाके एकदम नीचे की तरफ
annotate is there.
डिसेबल करना होगा सर आपको.
So annotate option is coming, but thing is like.
1 second, sir. I will show you. One.
अपना स्क्रीन शेयर करके बताओ सर को।
सर अब आपको स्क्रीन दिख रही होगी मेरी सर।
yes,
यहाँ पे आप गए, मोर पे आपको दिखेगा, नीचे आने पे डिसेबल पार्टिसिपेंट एनोटेशन।
ये मोर कहाँ है ये बता दो
अभी
सर।
जूम खुला नहीं है सर, अभी आपका जूम विंडो खोलिए।
थर्ड ऑप्शन पे आपको जाना होगा, डिसेबल
आपका जूम विंडो नहीं आया सर।
नहीं आ रहा है सर, आपका विंडो दिख नहीं रहा।
जूम विंडो शेयर नहीं है सर, शेयर करिए जूम विंडो।
जूम विंडो शेयर है सर, वो एक्चुअली जो एनोटेट वाला ऑप्शन है वो मैंने खोल रखा है, बट वो आपको शो नहीं होगा क्योंकि वो पर्सनल होता है सर।
अच्छा
हाँ, तो सर मैं ये बता रहा हूँ, थर्ड ऑप्शन जो आएगा सर, जब आप वहां पे जाएंगे एनोटेट पे और शेयर के बाद जब आप वहां पे क्लिक करेंगे,
नहीं
तो आपको
एनोटेट
वहां
पे
पे
कोई ऑप्शन नहीं आता सर।
थर्ड ऑप्शन दिखेगा सर, डिसेबल। आप फिर से शेयर करें सर। थर्ड ऑप्शन जो होगा सर वो शो करेगा, स्टॉप participant annotation.
Okay, let me go. Actually, that the annotate option is there, but that it give me that the many other menu bars like that, the drawing and everything over there. So it's okay. Let us go with this one. We'll see that.
Okay, sir. But again, it is like.
Sir, don't worry. I can clear that.
Okay. Okay. So. So objective of this lab is like that to understand that the basic of that the RF and microwave engineering through analysis and simulation of the various component and devices. So if you go with that this RF and microwave, we talk about like the many things like that, how to transmit that the power from that the one point to the other point, or how actually we are using that the basic RF component like that the waveguide or the transmission line, or that the let's say rectangular cavity, or any other filter and all those ones. So this lab is actually give you that the basic understanding of that the RF component as well as that the RF equipment. So this one is actually like that the non-classroom approach, and it is like that the components which are actually covered in this lab are the transmission line, waveguide, Smith chart. So let's say like we are talking about like all those the high frequency communication. So that the main challenges for the any high frequency component designing is like that the impedance matching, and the impedance matching will only be clear once that you understand that the concept of that the Smith chart, which actually provide you like that the what should be the required inductance or the capacitance you need to add in your system so that you can match your system. And then that once you know that the Smith chart like that you can use that the concept of that the impedance matching to use that providing the required impedance of the transmission line or the series stuff or the shunt stuff that will be actually covered in that the impedance matching. And then we are also talking about that this ratio meter or the scalar network analyzer. So that will also be used, but this is generally like the many engineering college, they are actually using in that the MTech first year, but like in IIT Kanpur, we are also having this experiment in that the BTech fourth year also. So the target audience for that our lab is that the third year and the final year UG and that the PG student, which could be that the electrical, electronics and communication, or that the physics. So physics people can also use that our lab. So microwave, whenever we say that the microwave, it is like the microwave, it doesn't mean like that the microwave is like that the wavelength is that the micrometer. It is like that the microwave, it means the micro is that the corresponding to the small, and wave is like that here like the microwave is the electromagnetic wave. So we could have that the many other wave, but here like that the concept whenever we use that the microwave, it is like that the small electromagnetic wave, and small is like the small wavelength electromagnetic wave. And where like that the wavelength varies from the some millimeter to that some centimeter in that order. So lambda, so lambda actually like that correspond to that wavelength, which is actually like the C by F, which is the 3 into 10 to the power 10 by F, and then actually we are taking the centimeter. So what happens that if we are operating at the low frequency, which is like that in the order of that the 1 to 100 kilohertz, and the wavelength, if I try to calculate, so wavelength comes at the 300 to that the 3 kilometer. So what happens that the circuit dimension are that the very small as compared to that the wavelength. So what happens that if you will actually try to measure that the voltage or current at any location on the circuit, so it will be actually like the same over there. Let's say that your circuit dimension is that the 10 centimeter, whereas the wavelength is like that the some 100 kilometer. So any point I will measure that my voltage and current, it will actually having that the same. So there will not be that any phase delay from the one point to other point. But if I go to the high frequency, okay, so negligible length, no phase difference is actually happening, and then you can actually use the concept of the lump circuit model. But if I go to the high frequency, let's say from the 1 to the 100 gigahertz, wavelength generally is in the order of the 30 centimeter to the 0.3 centimeter. So what happened that this if you are talking about like let's say that I have that some circuit which is like the 1 centimeter of the length, and at the same time that my wavelength is also in the order of the 1 centimeter. So you will have like this wavelength over there. So if I will measuring that the voltage at this point of the circuit, it will be the 0 voltage. If I measuring that the voltage at this point, that will be like that the some highest voltage, and then again it is going 0, then the negative of the voltage, and then again 0. It means like that from this point to this point, if I'm measuring under the circuit, which is like that this one is showing that my circuit dimension, which is comparable to the wavelength. So each point I will measure that the voltage, that will be that the different. So that the low frequency you can actually measure that the voltage or current, but the high frequency, if you're going, the measuring that the voltage and current become itself is like the challenge over there, because like the some point will be showing that the higher voltage and some point it will be showing that the lower voltage, or there could be like some phase change from the one point to other point. So that actually bring you that the concept of that the high frequency electromagnetic. So the difference is like that because phase is changing from the one position to other position. So based on that one, actually like that the people talk about the electromagnetic theory or the transmission line or the waveguide. So those are actually like that the part over here. So it shows like that from the voltage we should actually look for the electric field, and from the current we should actually look for the magnetic field. So based on those concepts, actually like that in this one we have actually proposed that the 10 experiment. So I will go that the one by one. So the first one is actually talking about that the various mode in that the rectangular waveguide. So I'm having like that my you can actually the way this will work. So what actually like that you can choose that the what should be that your operating frequency and what should be that your mode. It will show that the various mode pattern over there. So currently like that if you go with the book, you will only get like the some fundamental or some dominant mode over there, or with like 1 or 2 more modes over there. But this whatever the lab we have developed, you can go for the any mode indices. Like you can see like that if I have that the T57 or the T53 over there, or TM23 over there. So what should be that the mode pattern? So those things will be getting. So it will give you that the electric field pattern, it will give you the magnetic field pattern, as well as that it actually give you that the surface current distribution. So all those part actually you get using that the this one. The second experiment is like that the waveguide cavity. So the generally like the rectangular waveguide that is open from both the side, but here like that if you will short that the both the waveguide, how that the electromagnetic field will be actually changing inside that the waveguide. So those concept is actually explained in that the experiment 2, where actually like that the I'm having that this electric field lines which is actually going like this one, and I'm having that those like the where actually you'll be getting the electric field maxima, where it will be giving that the minima, and how that the magnetic field look like, or how that the surface current distribution will look like. So those problem is actually explained in experiment 2, and I'm planning to demonstrate you today that the some 2 to 3 experiments, which actually I will let you know that the complete procedure that how that the labs are actually developed. So I will go here fast, and then that I will actually try to demonstrate 2-3 labs. So measurement of that the dielectric constant and loss tangent. So this is another thing is like that the what is like that the application of that the rectangular cavity, why we actually talk about the rectangular cavity. The advantage is like that the once you understand the concept of the rectangular cavity, you can determine that the any electric property or any magnetic property of any substrate or any material. So those concept is actually introduced like that. Sometimes we don't know the why we are actually studying that those topic. So here like that it shows you like that the once I understand that the concept of the electromagnetic field, so that will actually give you the like that the you can actually decide that this should be like the my dielectric constant or loss tangent, and then you perform that all those simulation over there, and then you will try to see that at the end of that the thing that these are like the my dielectric constant, and that will be actually like that the loss tangent over here. So these are like that the some sample you will insert in that the rectangular waveguide, which could be the rectangular or the circular. You insert over there, and then you perform that the experiment. And after that one, you will actually try to determine like the what will be the material property of this data. Okay, so generally like that this frequency change in that the resonant frequency of the cavity correspond to the epsilon r prime, and that the change in the epsilon r double prime will actually give you that the quality factor. The fourth one, this one also actually I'm planning to demonstrate today. This is like that the if you are having that the some transmission line over there, and if I launch that the voltage, and this is like the my source generator. So what will happen like that the moment I will launch that the my voltage, this voltage will actually see that the so currently like that this voltage assume that the my transmission line is like the infinite transmission line. So it will see that the input impedance same as the characteristic impedance. So some voltage will be actually launched and it will actually travel on the transmission line. But then at that the load, it see that the change in that the impedance. So there will be like there is some reflected voltage, which will actually going back to that the source over there. Okay, so this voltage will be actually going back to that the source. So this is actually experiment we actually perform in that our UG also. So that is actually like the independent of like the DC or that some low frequency or high frequency, that is actually phenomena. But at low frequency, all those things actually the transit happens so fast. Actually, we don't realize like that it is actually making that the some shift, some change in that the voltage. So I will go and explain like the what is this experiment, which will be actually giving that the transient response of any transmission line. So it could be the DC or any fixed voltage which you actually apply on the transmission line. And in actual experiment, you actually connect that the CRO at this one as well as the source, and try to measure that how the voltage is changing with the time. So this will be like that the some curve will be getting on that the CRO. Experiment 5 is actually like that the if I will be actually looking at the so that was like that the if I give that the DC signal, and here if I will be giving that the frequency AC signal, and that could be like that the some low frequency or the high frequency, and how that the moment that you will actually apply that the AC voltage on the transmission line, how that the standing wave pattern is forming on the transmission line, and if the standing wave pattern is actually forming on the transmission line, what could be the challenges in terms of like the measurement of the voltage and current, and then the why that then we go actually and try to design most of the circuit at the high frequency, which measure that the incident and the reflected power instead of the measuring that the incident and reflected voltage. So that concept is actually very well defined in that this experiment. Experiment 6 is like the Smith chart. So this will try to introduce you first like the what are like the various circle which appears on the Smith chart. Where is the short circuit point? Where is the open circuit point? Where is constant resistance circle, constant conductance circle? Those point will be actually, so the first experiment on the Smith chart will be the introduction of the Smith chart. And the second one is actually like that you learn about the matching. Okay, so how actually you can provide that the matching on the system, and that is like that the very unique like that where actually that once you are actually matching that the circuit, you can really see on that Smith chart what is happening. So that is like that the very unique experiment which we have designed, that experiment 7 over here. Then we also introduced the concept of the S parameter. Like so that's why I said that we don't measure like the voltage or current, we actually measure that the power. So here like that what is like the S11, which is that the incident. So this is like incident electric field. This is the reflected electric field. So S11 is like the reflected over incident electric field, and here the S21 is that the transmitted over that the incident electric field. So this experiment will actually give you the concept of that the scattering parameter. Instead of that the low frequency, we define that the parameters which is called like the Z parameter or impedance parameter or the admittance parameter or H parameter. But the high frequency, we define that the S parameter called as the scattering parameter. So this particular experiment actually introduce you that the S parameter for that like the N-pole system. Experiment 9. So this actually try to find out like that the if I have that the design some transmission line, and if I'm changing that the dielectric which is filled between that these two conductors. So this is that my center conductor, this is like my outer conductor. So if I will change that the dielectric in between or change that the diameter of the inner or outer one, how that my characteristic impedance will be actually changing, and the moment the characteristic impedance will be changing, the overall matching of your system will also get affected over there. So that will be actually covered in this experiment. Experiment 10 actually talk about that the ratio meter are also called like that the scalar network analyzer. So like that the low frequency we actually use that the system which is called like the CRO, that is that the or the digital oscilloscope now people are actually using. But at a high frequency, you cannot actually measure that the voltage or current. So you generally measure that the what is that the reflected or what is that the incident power. So people actually define that the scalar network analyzer or the vector network analyzer, which will give you that the magnitude as phase information. But generally like the scalar network analyzer, which give you that the what is like the incident to the reflected energy, or what is the transmitted as compared to the reflected one. So scalar network analyzer, it is like that the if you are having some component in your lab, you can design that your own scalar network analyzer. So this will be actually concept over there. So I will actually not actually explain. Instead that I will actually take that the sum of that experiment. So you will see that here that the sum link is actually given. This is like that or you can actually write on that the Google that the RF and microwave characterization laboratory. So it will actually bring you to that our home page, which is actually looking like this one. So this is that the virtual lab IIT Kanpur RF and microwave characterization laboratory. So and there like the list of that the experiment which I was explained. So this 10 experiment is actually given over here. So if you go that any of the experiment, so initially actually if you have not created that your login, so it will first ask you to that create your login, and the moment you have actually created your login, you can actually go inside of that this website. And so let me go with that list over there. So maybe like that I want to demonstrate that this one. So what will actually like that it will give you like that what is like that this experiment. Then you can read actually like the theory related with this experiment. So it will give you that the step by step like that what is like the concept, what is actually happening over there. So let's say that this experiment I will be demonstrating. So I will actually explain something like it will give you like the logic like that. Let's say if I have that this is the transmission line, I'm applying that some voltage over here. This is my generator resistance, and this is like that the transmission line. So initially, once the moment you actually launch that the voltage at this point, your voltage source doesn't know that what is that the length of the transmission line. It only sees that the transmission line as the infinite transmission line. So what voltage it will be actually launched? So the launch voltage will be like the V naught into that the whatever that this characteristic impedance. Let's say it is that the Z naught. So V naught into Z naught over that the RG plus that the Z naught. So that will be that voltage which will launch over there. It will be actually traveling on the transmission line. And let's say that if you will cut that transmission line and put like the somewhere on the transmission line that the some voltage you want to measure over there. So initially like that the voltage wave has not reached from this to this location. So initially the voltage will be 0. But the moment that the voltage will reach to this position, you will see the change in that the voltage. So initially like if you are measuring the voltage on the CRO, initially it will show that the 0 voltage, and after some time you will see that the change in the voltage. And then it will be actually the voltage will be traveling. If it is the match system, same voltage will be maintained. Otherwise that the voltage will be actually like that the the reflected voltage will come, and that it will go back. So like you will actually go and read that the complete theory for the each experiment, whatever like that. So you can go all along. So it will make you understand that what is like the theory behind this one. Then you'll go to the procedure. So if you go to the procedure on the left side, there will be like the different VIs are there, which is like the .exe file, which is made from the virtual lab. So here it is like the runtime engine. So it is like the free software which you can actually download from here on your local system. Install this software, which is the software name is called like the LabVIEW. This is like my LabVIEW runtime engine. And once the software is installed in your system, then you can download the experiment file. So for this one, there are some experiment file are there, which actually you can download. And after downloading, you can run that one. And the moment you will run, you will get like that. So this part, procedure part, actually explain you how your how actually you are supposed to perform the experiment. So it will actually tell you like that you are supposed to give this part, which is actually like the input parameter, and what could be the output parameter, how your screen will look like. If these are like some default input parameter, will put what should be the result. So all those part is actually given in this the procedure part. So once you will read the procedure, then it says that a small quiz, like you can actually attempt the quiz just to understand whether you are having enough knowledge to operate this experiment. Then you can go to the tutorial. So for some experiment, it is the PDF tutorial. Some experiment, it is like the video tutorial also there. So you can download this video and you can run. So it will be actually show you like how the experiment will run on your local system. So it says that the manual. So this is like you can also read the PDF manual about the experiment, about the procedure. And these are like some reference also given, like from where like this concept have been given. So if you want to refer in more detail, you can go to the book. So the thing is like you can go to the procedure and download your experiment from this one. So I will actually try to demonstrate the sum of the experiment which we have designed. So the moment you will download, it will actually create this type of the file, which is called like the exe file. So let me show that the sum of the exe. So I'm actually running this time domain thing. So on the top of the screen, you will be actually getting this one, like this what the experiment you are performing. So it says like there are source specification you have to actually provide. You have to give some observation specification. Observation specification is like how long you wanted your simulation to perform, or like that sometime like the way you are actually looking that the simulation response that is going in with the time very fast, you can actually slow down your experiment. Okay, so let's say first go with this part. So so here this is my transmission line, this is my voltage, this is my generator resistance, this is my load. So this is like one of the easy experiments which actually I try to explain you, and then you will understand also that how to run the other experiment. So here that it says that the source specification. So you are having this source, it says like that you can define the source voltage. Let me define that the 20 volt. Source generator resistance, I am defining that the 50 ohm generator resistance. What is that the load specification? This is like my load specification. I will say that my 50 ohm system. Okay, so number of cycle how long I want to see that on the screen, like that my voltage is going on this side, then the coming back or going back over there. Location of the point where you are actually measuring that the voltage. So this will be the actual experiment you can also perform, but here like that I can say that I'm measuring that the voltage at the source location itself. Like the source and my oscilloscope both are actually connected at the input of my transmission line. And this is my transmission line specification, like that I'm taking 100 meter of the length of the transmission line. 50 ohm is that my characteristic impedance, some relative dielectric constant, I'm taking the 9. You can also take some other number. So these are like that my input parameter, these are my input parameter, and here that my screen is like that the output parameter. So I will explain that what is this screen. So it's saying the voltage wave traveling on the transmission line. So this screen is showing like that my transmission line length, which is actually like the 0, and this is like my transmission line location at the 100 over there. So on the x-axis, this is the distance on the transmission line is plotted, and on the y-axis that the voltage is actually plotted. So on that, once I will run the experiment, you can see that with the time how that my voltage wave is traveling on the transmission line. Whereas that this window, it says the total voltage measured at any point on the transmission in respect to the time. So this is like that if you actually perform this experiment, what you see on the CRO screen. So it is like that with the time. So this axis is the time and this axis is the voltage. So I'm looking at with the time how my voltage is changing on the transmission line at any fixed location. So let me run the sum of the experiment, then it will be clear to you. So I'm launching the 20 volt over there. 50 ohm is my source resistance, and 50 ohm is my characteristic impedance. So what will happen? Initially that the transmission line will say that it is like the infinite transmission line. So this 50 ohm I will launch. So this is like 20 volts. So 10 volt will be dropped across here, and the 10 volt will be dropped across there. Okay. And then this 10 volt will be traveling on the transmission line. And if because the RL is also same as my characteristic impedance, whatever the wave will be coming, it will be actually absorbed over there. So currently it is not the high frequency concept. It is like that the even low or DC voltage we are actually running this experiment. So this concept is that the concept of the reflection coefficient is not only exists at the high frequency, it also exists on the low frequency. But all those things happen so fast that we don't realize over there. So let me run. So you can see that I am actually looking at this line. So I will run again. So this is like my 10 voltage I have launched on this transmission line, and it is actually traveling with the time. And then the voltage goes this 10 volt and it is absorbed over there. And similarly like that if I see that this is screen, so initially because I'm actually measuring at like that the location which is actually like the 0 location over here. I'm measuring at the input of the transmission line. So I will actually find that this 10 volt that is immediately reaching to my source of the point, and then it is actually continuously maintained over there. But let's say that instead of the 50 ohm reflection coefficient, I'm taking the 100 ohm of the load resistance. Sorry, load resistance is now 50. So what will happen that there will be the impedance mismatch at the load end. So if I launch the voltage over here, so 10 volt is launched because it sees that the source is at the source. It will consider that the transmission line length is actually like that the infinite. So it will see that the 50 ohm, so that the 50 ohm is 10 volt will be dropped across here, and 10 volt will be dropped across there. So it will be like that it will be dropped. So this 10 volt is actually moving over there, and then it actually hits this one, and then it is actually coming back. So depending upon that, what is their reflection coefficient, which is like the ZL minus Z0 over ZL plus Z0. So the gamma L you will find, and then this reflected voltage will be coming over there. Now reflected voltage which is coming over there, it will be actually absorbed by this side, because the 50 ohm line it was there, and the source resistance was again the 50 ohm. So the 50 ohm, because of this one, whatever the voltage that was reflected from the load in and coming over here is absorbed by the source resistance. So this actually happens for any circuits on the electrical circuits, whatever like the electrical, it is respective like that whether you are the electromagnetic energy engineer or you are electronics engineer or physicist. This happens for any transmission line whenever you are using. So now also if you see what is happening, the source resistance is the 20 ohm, this is like the 50 ohm, and this is the 100. So what should that be the voltage at the RL? If I am actually like that the low frequency engineer, how actually I will calculate? I will calculate like that this 20 into 100 by 100 plus 50. So it is like that the 100 over 100 plus 50. So this is like 2 by 3. So so V naught is like that the 20 volts. So 20 into 2 by 3, which comes to be like that the some 13.3 volt. So that is like the voltage. So at the low frequency, if you go and measure that everywhere that the voltage, I will actually get like that the 13.3 or 13. So whatever the 13.3 volt, actually I will get that the all over that the place over there. So this actually happens on the transmission, but this happens in that the very few. So this happens that within like that the 2000 nanosecond or that within 2 microsecond, and that's why like that we don't realize. So let me show that again. So initially like that on CRO it will measure that the 10 volt, and the voltage is actually going and it is coming back, and I'm measuring at the source. The moment it will reach to that this point, I will see that the change in the impedance. So initially I was measuring that the 10 volt at the input of the transmission line, and but after some time I will measure like the 13.3 volt on the transmission, and that will be actually maintained there. So at the low frequency, actually like that we don't care about like the what is happened within that the some few microsecond. Okay. So where like the time period, like the, let's say even that the 50 hertz you are talking about, which is like the normal our time, the frequency part, which actually come to like our home supply, which is like the 50 hertz. So we don't care about like the what is happening. So it is like the time period some millisecond, and all those things happen at the some microsecond. So we don't care that all those things, but that actually create that the issue once you are actually doing on that the high frequency. So currently like that I have taken that this one source impedance same as that my generator impedance. Only the difference is that the RL is different than that the R0. But let's say that I will put the RG also different than the R0. So I'm putting that the 100 over there. So if I am actually like the low frequency or that the low frequency engine, what will I measure? I will measure that this 20, so 100 ohm resistance over here and 100 ohm resistance over there. So I should measure that the 10 volt and the 10 volt over here. Okay, after some that once the transient will be over. But this is actually happening not immediately. It takes actually that the some time. So let me run. So what will happen that this 100 volt and this characteristic impedance 50. So initially it will not launch that the it will assume that it is like that the 100 ohm all over that the place at the input over there. So the voltage which will launch is like the 50 over that the 50 plus 100. This is like that the 1/3. So it will be like the 6 volt, close to 6 volt, which will actually launch, and then there will be like some transient will be happening over there. So it is like the 6.6 volt is actually launched. Then that it will be reflected over there. It is coming to that the source. Again that the reflection is actually happening, going to the transmission line. So all those transient is actually happening. And after that, you will see that after some time it will go and saturate at that the 10 volt. Okay, but all those things actually happens that the infast. Now that if I will actually try to measure on the CRO, so how actually it is happening. So let me actually stop and run again for you. So this is like that I will measure the 6.6 volt if I measure the input of the CRO. And this is within that some nanosecond if you can measure. Then you will see that the change in the voltage. So this wave is now going. So still you will measure the constant voltage, and the moment it goes hit to that your source, and you will change that see that the change in the voltage. Okay. So you ultimately get that whatever that was the desired result, like that if this is that the 100 ohm and this is that the 100 ohm, ultimately like that if I will measure that the voltage, it should be that everywhere on the transmission line or across the load that the 10 volt. But 10 volt that doesn't come immediately. It is like that the voltage actually see that the initial transmission line, infinite transmission line go travel based on the characteristic impedance reflected back, and then it is happening. And similarly like that whatever is like the current wave is traveling on the transmission line, that you can see on this window. So I will actually stop over here. You can actually play with that there are n number of things which you can click that the voltage you can change, number of cycle where you want to see. You can play with that the length of the transmission line. You can play with the characteristic impedance. You can play with the relative dielectric constant, and you can come out with the various response. So you can, like if you are faculty, you can actually give that the assignment based on this experiment. If let's say that this is my voltage and this is my source resistance, and this is my load resistance. So try to measure that the voltage at the load end. So currently I'm measuring that the voltage at the source end. You can also measure that the voltage at the load end and see that how the voltage is changing with that time. There could be that many assignment can be created based on this experiment. So I will stop here. I will actually take that one more experiment, which is like that if you are actually applying that the AC signal instead of that the DC signal. So I will actually. So this is like some observation specification which actually see that how that you are looking to the wave. Here like that I have that the incident voltage, whatever the frequency I'm applying. So it is like that the some gigahertz. So it is like the some 30 megahertz signal I'm applying. This is my load resistance. So let me take that the 50 ohm. Because the AC signal is there, so here you have the flexibility. You can actually also give the input as the complex load. Then this is like my transmission line length, characteristic impedance, and the relative dielectric constant. So this screen shows that what is the incident voltage on the transmission line. This one is the reflected voltage on the transmission line, and this is the total voltage appearing on the transmission line. Okay. And this one is like that the very uniquely designed lab where actually like you try to explain that the student that what is the standing wave pattern. So sometimes they don't understand what is the standing wave or what is like the reflected voltage, or how like the mixing of these two will actually change the overall performance of the system. So that will be like the very good concept. So here you will find that this is my incident voltage. The 15 volt is actually launched and it is traveling over there. And currently I have put like that my load impedance is also like that my 50 ohm. So you will find that there is no reflected voltage which is actually generated. Okay. So this is like that my voltage that is appearing on the transmission line. Okay. So one thing is like that you will also get the concept. This is distance on the transmission line. This is the 40 meter of the length of the transmission line. And 40 meter length. And then I'm actually applying the 30 megahertz signal. So you will find like that within this one, if I will measure that the voltage at the some point, so in that with the time it is changing with the like at particular distance with the time you will find like that the voltage is actually changing. So at a given instant, if I will be measuring that the voltage at a different location, it will have actually like the different voltage. Other thing is like that if I will not provide that the match system, if I will provide that the let's say that the some 100 ohm over there. So this is non-matched system. Characteristic impedance 50 ohm. So I will have that the reflected voltage. So now that the moment it will reach to the load, you will find out that this red one, which is actually like that my reflected voltage over there. Okay, and now that here on this screen, you will see that the standing wave pattern. So this has like the component of the standing as well as the propagating wave. So you define the concept of that the voltage maximum, the voltage minima. So like that if I will measure like somewhere here, where is my cursor, I will always measure that my voltage, which is actually like that some maximum amplitude over there. But if I will measure that somewhere here, you'll find like that the voltage is actually like that somewhere lower over there. So it will be more clearer like that if I will give you that the perfect short circuit over there. So let's say that if I'm actually shorting that at the load line and giving that the AC signal. So what is happening? Okay. So this one is like that my so now like let's say what is the challenges over there. If I am measuring the voltage at this location, where is my cursor is pointing, I will always measure that the zero voltage. It is not changing with that the time. Okay, whereas like that if I'm measuring over here, I'll be measuring like that the voltage is going to maxima 0, and at the other side that it is going the value, and then it is coming back. So if I measure that the voltage at this point, it will be different. If I measure that the voltage at this point, it will always be coming the 0. So this actually gives that the concept to that the UG student, like what is the challenge if I go to the high frequency. Okay, so the main problem is like that if you go to the high frequency, if you are measuring that the voltage, so because of that the standing wave pattern, you will find like you may measure that sometimes the voltage at a location where that the zero voltage is forming, or you may measure that the voltage where actually like that the maximum voltage is actually forming over there. So this is like the total voltage, and then it will be actually amplitude of the voltage. So let me run again. So this is like the amplitude of the same thing, this curve. So that will be actually shown over here. Okay, so you can see that this one. So this is like this is the voltage minima location. This is like my voltage maximum location. So if I'm measuring the voltage here, okay, let's say with the CRO, I want to measure that the voltage. If I connected that somehow here at this point on transmission line, I will always see that the zero voltage. But actually, like that, there is the electromagnetic energy which is actually flowing in the direction. So that is actually, you can actually explain this concept to the student, and student can also actually play that with the various number and try to see if it is like that the match thing. So it is not happening over there. I can also give like that the infinite impedance. So let's say that like that some very high impedance. Then also like that I will having the reflection coefficient which is 1, or like that I will get the pure standing wave pattern. So that concept also you can actually explain. So either it is like the pure short, or it is like the pure open. You'll be actually getting that those standing wave pattern. Only thing is like that if it is like the open, so at that the load location I will getting that the maximum voltage, and then at the lambda by 4 I will be getting that the short voltage over there. So this is actually explained in this one. So you can also explain like what is the difference between the short circuit and open circuit at the high frequency. Okay. So though the reflection coefficient will be same, but their phase will be different. So for the short circuit, reflection coefficient phase is at the 180 degree, and for the open circuit, the reflection coefficient phase is at the 0 degree over there. So this is like the one of the experiment. Then other one is like that if you are actually like the RF engineer, you should understand that what is Smith chart. Okay. Many college actually it is now included under the part of their UG curriculum. So generally like that you don't find like that the many experiments on the Smith chart, but here like that we have created that the experiment on the Smith chart. So a student can actually play with this various thing. So first thing is that the student try to understand what is actually the Smith chart. So this is like that about the first experiment on the Smith chart. So this is like that my constant resistance circle. So these are like the Smith chart. So this is like that my zero R equal to the zero circle, and then I can actually take like that when the R equal to 1, how my circle will be forming. R equal to 2, R equal to 3, R equal to 4, or let's say that some number, let's say 1.5. Okay, how it will look like at the 0.5. Okay, so those one. So you can actually understand that these are those constant resistance circle, how it will look like. Then I can go and understand the constant reactance circle. Now the reactance can be the positive or as well as the negative. Like it could be like that the real load, or it could be complex load, and the complex load it could be inductive or capacitive. So if it is inductive load, you will be getting that the plus J. So it is the plus J1, plus J2, plus J3. So this will be actually teaching you that what will be the constant reactance circle. And then it will be like a minus J1, minus J2. So you can actually also see that minus 2, minus 3, minus 4 over there. Okay. So this will teach you like that how the conductance circle will look like, and how that the conductance or the reactance circle will look like, and constant resistance circle will look like. Then they can also understand where is the short circuit point. So it will show that if it is the impedance chart, you are having that the short circuit point over here. You have that the open circuit point at this location. Or let's say like that I want to understand that the VSWR circle. So VSWR circle is like that I will consider that wherever that the R equal to 1 circle is cutting this real axis, that is like the center of the Smith chart. And then from there we actually draw the constant VSWR. So VSWR 1 means like your system is actually matching, like the people who are working in this antenna engineering or the microwave circuit, they understand that what is the VSWR. So it will actually showing that if the VSWR is 1, your system is completely matched, and that looks like that at this point. Or if I will, if I actually I can choose that the some number. So VSWR range is generally from that the 1 to infinity over there. So you can actually change that the number and see that how my VSWR circle will actually look like. Okay, so this is like the other part of that my VSWR circle. I can put the some decimal number also like the 4.5 or this thing. Then it comes to like that the load point. So I have given like that my load, this is like 50 plus 50. So if you normalize that one, it will come like the R equal to 1 and J equal to 1. So the intersection of that the constant resistance and the constant reactance circle will give you that the point which is will be representing that the load point on the Smith chart. So it is like that the 50 plus 50, which is representing that the 1 plus J1. So this is like the my point. And corresponding to this point, I can draw that my VSWR circle. So this is like that my point on that the. So this is like that you will never find anywhere in the world this lab, whatever we have designed on the, which is actually treating on the Smith chart. So this is like that my VSWR circle. I can switch off, I can switch on that my VSWR circle. Corresponding to that, this point, I want to see that the admittance. So admittance will be like that a 180 degree off to that my impedance point. So the moment I will switch on, so it shows like that this is like my admittance point. It also shows like that if you know that the impedance on that the Smith chart, how actually you try to find that admittance. So you will take that this point at the center, draw the circle which is passing through the load point, and then from here joining this point, if you draw that this line which will be actually representing that the admittance. So admittance is like the 180 degree off to that my impedance circle. So that is like that the impedance. Then we talk about that whether you are moving towards that the load or towards that the generator. So I want to see, so it said yes. So let me switch off that this one admittance. So this is my load point, and I'm moving toward the generator. So toward the generator on the Smith chart is moving like the clockwise direction. So you can see that this is like from this load point, if I'm traveling on the transmission line, how actually I'm reaching to this point over there. So depending upon whatever the length of the transmission line you are using, you will be actually at that will be like the input impedance of your circuit. Or if I will actually move to like the 0.5 wavelength, so you'll be actually getting like that at the same point. So it shows like that my Smith chart is normalized for that every lambda by 2. Or I can also say that at the high frequency at every lambda by 2 distance, I will be getting that the same impedance. So those concept is also actually it can be explained from here. Then similarly like that, I want to see that the wavelength toward the generator, so which is like that the anti-clockwise movement on that the Smith chart. Okay, so you can see like that you are moving on the Smith chart over there. So this is one experiment, and then I will show that the impedance matching, and then I will close this session. So a single step.
So meanwhile, if participants have any questions, so you can raise hand. We will allow you to speak.
Yeah, so this one is like that the matching of the thing. So this one is like yes, Manisha ji. Yeah.
So can we take a question?
Yeah, please go ahead. Please go ahead.
Thank you, sir. Yatin, I am trying to unmute you. Please ask your question.
Good morning, sir.
Good morning.
So I am asking where we can implement this Smith chart applications in real-time application.
So let's say if you're designing that the any RF circuit, okay, any RF like which is like there are some high frequency circuit is starting from the few megahertz, and that let's say 2.4 gigahertz or any 5G thing or any 4G thing. The challenges for any high frequency circuit is that the impedance matching. So once actually you know that what type of the inductor or the capacitor should be actually connected to match that the impedance, then only that your circuit will work. So the impedance, this Smith chart will give you that what should be the required amount of the inductance or conductance should be added So those, for that one, that this is actually used, that the Smith chart. So that is like that the thing, like so any circuit, like any RF circuit you are designing, that the challenge is that the impedance matching. Okay, so I say like that I have that the impedance of, let's say that the 100 plus J100 over there, and I have that the 50 ohm of the transmission line, or that the source impedance is the 50 ohm, and I want to launch that the maximum power to that this load. What will happen that because source impedance or the transmission line impedance is not same as that your load impedance, so whatever the power I will launch, most of the power will reflect back to that the source. It will not deliver to that your load system. So there should be that some additional capacitance or inductance need to be added, and which will actually take care of that this matching part, and so that the power which you launch, that should be delivered to that the load.
Yes, sir. Thank you, sir.
Okay.
One more raised hand as I can see, sir.
Yes,
Rohit Vishwakarma. Please ask your question.
Hello.
Yes, sir.
Yes.
Good morning, sir.
Good morning, Rohit.
सर कह रहे हैं कि what is advantage of RF circuit?
What is the advantage of RF circuit?
Yes, sir.
So you are using that the mobile.
Yes, sir.
So mobile is that the RF circuit or not? At what frequency it is actually operating? So mobile is generally operating at that the 2.4 gigahertz. Okay.
Yes, sir.
Okay. So anything you are doing under the mobile, or you are designing the base station, or you are using that your Wi-Fi network. Okay. So most of the thing is like the high frequency thing, and if you are designing that any of the high frequency circuit, this concept will be actually needed. Without this concept, you cannot actually realize anything. You think of that the mobile, or you think of that the Wi-Fi router, or you think of that any communication system, they cannot be designed.
Yes. Thank you, sir.
Thank you.
Okay.
Yeah, Manisha, you can allow that the more question like that.
Okay, sir.
Yes,
Actually, we are having more UG students, so they are asking basic questions, sir.
Yeah, please go ahead.
Yes, sir. Thank you, sir. Any more questions from participant side? Please raise hand. We will try to speak you and ask your questions to Vaibhav, sir. Please raise hand. Sir, I think there is no more questions, so please continue, sir.
Yeah.
Okay.
So this it is not only like that this communication. Even let's say that you are talking about that your DTS system, that the cable network now you are actually looking, okay, which is actually now receiving that the signal directly from the satellite. All those are actually the high frequency, except like that the low frequency, which nowadays like that there is power transmission, or you are using that your electric appliances at home. Even that the electric appliances you consider the microwave oven, so this is actually that the high frequency, and they start at the low frequency. So all those one is actually like the high frequency. Even now, if you are discussing about that this processor, whatever the computer or the laptop you are using. So if you remember like that they say that the clock speed, or like the Intel 2.4.44 gigahertz, or Intel 3.4 gigahertz, or i7 or i9 or i10 are coming. So if you see that their clock speed are actually changing over there. So now the people are actually going that the high frequency, even all those processors. So even now to design that the even electronic processor, you need that this RF background. So for that one, you need to have that the knowledge of the transmission line. You need to have the knowledge of the Smith chart, impedance matching. That is actually required, or how that you will launch that the wave from the source to that your actual load. So the transmission line concept will actually come. Okay, so let me complete that this part. So this one is like the Smith chart. So this is like the point over there, and on the Smith chart, so it will be actually like the load. And my objective always in the Smith chart is that I have to come to this point on the Smith chart without losing that any power which is actually transmitted from the source. So this one is like the inductive load. So what happens that from here I have to come that here. So two things. One thing is like that I travel on the transmission line, okay, which is actually almost moving on the constant VLW circle. And another point like that we have to add that this stub. which is like that on the actual circuit, once you are designing the RF circuit, it is like that my load. So at what location I have to connect that my inductor and capacitor. Okay. So that's why that the low frequency you can connect that your inductor and capacitor at any point. Okay. Whenever you are actually, let's say they are discussing that the maximum power transfer and all those things, you say that it should be the complex conjugate match. Okay. So if it is like the 50 plus J50, you will actually say that the 50 minus J50 will have the complex conjugate match. But at the RF frequency, it is not only like that what value you have to connect, you have to also see that at what point you are connecting that load. So that is very important in that the RF circuit. So first thing is that if this is that my load location, I will try to find out that where that I can connect that my inductor capacitor, and this will be like that my inductor or the capacitor. So high frequency, you actually don't realize the actual inductor capacitor. It will be that any transmission line terminated with that the short or open, that will contribute to that the inductor or capacitor. So this is like the concept over here. So this is my load point, and ultimately my aim is that come to the center of the Smith chart. So this one is like that the location of the stub. So from the load in, so from the load in, I am trying to find out where I have to connect that my stub. Stub is like the inductor and capacitor in the low frequency term. So if I'm changing this length over there, it shows like that you have to come at this point. So this is my location, and after that I'm actually adding the capacitor inductor. So this will be showing that how you can come over that on the Smith chart. So this is like the point I have to come. So now here you can read that where actually you have to connect that your stub, and here it said that what should be that your length of the stub. So actual length, if you try to solve on the Smith chart, it shows over there. This should be that my length of my stub. Okay, and you are having like the various option. You can actually take the open circuit. You can take the short circuit. You can change your characteristic impedance in this experiment. You can also change the load impedance over there. I mean, like you can actually work with whatever the desired load for you. So this was actually part, and there are some more labs are there which actually you can use to understand the experiment. So I will finish the session here. Manisha ji, I can take some more question if student or any other faculty member are having any question.
Okay, sir. Thank you so much, sir, for such a nice and informative session. Now I will take questions from participant side. Participant, please avail the facility of raise hand and ask your questions. Students, please ask questions.
You can ask the general question also related with the low frequency, high frequency, or any communication thing.
I am unmuting Ankit Mohan Pandey. Please ask a question.
Hello, sir.
Hello.
Hello, sir.
Yeah, please go ahead.
Sir, can you repeat the last session, last topic?
This Smith chart?
Yes, sir.
Okay. So that you want the introduction of the Smith chart or this matching part?
Sir, अभी show नहीं हो रही है.
Okay, so let me show that.
सर आपने ये जो RF वो वैल्यू निकालने को बता रही थी वो चीज क्लियर नहीं हो पाया.
This one?
जी सर.
So let's say like that you are having the source you are connecting over there, okay, and this is like that your load impedance. So let's say that your source is that the 50 ohm source, your characteristic impedance is also that the 50 ohm, and your load is somewhat different than the 50 ohm. Let's say it is like the 100 ohm or 100 plus J100 ohm over there. So what will happen that at the high frequency there will be like the impedance mismatch. Okay, and because of the impedance mismatch, there will be some power which will be reflected back to the source. So whatever the power you want to deliver to the source, that will not be delivered, even that the some of the part of the power will reflect back to the source, and the rest power will be dissipated within that the load. So to avoid this one, at the high frequency, people use the concept of that the impedance matching. Okay, so let's say if it is like the 100 plus J100 ohm over there, so I have to actually match that the system such that the matching system should not be having that any power dissipation. It means that we can only use that the inductor and the capacitor element to match that the system. Is that okay? So you are getting like that if low frequency, if I said that I have the complex impedance of the 50 plus J50 and your source impedance is like the 50 ohm, what you will do at the low frequency or the maximum power transfer, you actually add that the minus J50 ohm of that the capacitance in series with that your source, so that they will actually cancel each other and the maximum power will be delivered to that the load. But at the high frequency, it is not only that the adding that the capacitor and inductor, it also becomes the important that the where you are connecting that your inductor capacitor. So from the load location where actually you have to connect, that is also become that very important, because in the high frequency, even from the one position to other position, if I'm going, my phase is actually changing. Okay, so you have to find out that for this corresponding load, at what location I have to connect that my capacitance, and at what should be the value of the capacitance or inductor, so that I can deliver that the maximum power to load. So that thing is actually trying to find out like that at the high frequency. And then that to design this one, you have to use that the Smith chart. So that is like the thing we are trying to explain.
Okay. Thank you so much, sir, for explaining all the things. Now, another questions, as I can see, Arnav Singh, I'm trying to unmute you. Please ask your question. Arnav, please unmute yourself. Yes, you are audible. Please ask your question.
Good morning, sir.
Good morning.
सर जो हम लोग अभी वीडियो देखे हैं इसका अगर बाद में देखना चाहें तो कोई लिंक इसका सर?
No, you can actually go all those things, and that for each experiment there is that the video is also there, like the how to run that the experiment. So you can actually download that the PDF file, and you can actually run that experiment, as well as you can download that the video file and see that how the experiment you can run. So both are there on that the website.
Sir, किस website पे है?
I will show that the website. So either you can go and write like that. I will also go and write. Let's say that I will go under the Google and write at the RF and microwave characterization lab. Okay. So I will go and put that this thing, RF and microwave characterization lab. This is the first link you will get on that the Google, and this will be actually like the lab where you will find that all those things. Okay, virtual lab, RF and microwave characterization lab. So there that you will get that all those experiment, how to perform the experiment, theory, procedure, quiz, reference, video tutorial, everything you will get on this website.
Okay, sir.
Okay.
Okay, sir. Another raise hand, as I can see, Neetu Mishra. Neetu, please unmute yourself. I have allowed from her.
Hello, sir.
Hello.
Sir, why we prefer to use RF technology while making project in which we use a remote to control the movement of your robot to find out metals or something?
So what happened like that at RF technology, it is mainly actually like the electromagnetic wave, and the once that the wave travel from the one medium to other medium, it characteristic it's different. Like that if let's say that if it is traveling in the one medium, if the phase velocity will be different, or like that the overall the relation of the electromagnetic field, like that we say the intrinsic impedance. So they are actually like the different. So for us, it will be very easy if I want to determine that whether it is like the metal or whether it is the dielectric, or so either it is for the detection, because that the wave phenomena is that the different for the different material. So it will be easier for us to determine that whether it is that the metal, or whether it is that the wood, or whether it is like that the let's say plastic. So that will be very easy. And other thing is like that the let's say you want to communicate to the robot. So if anywhere that if you want to have the communication link has to be established, that has to be the RF link, because that at the low frequency you cannot have that those communication link which you can establish, because that your wavelength is that the very large, and at such a large wavelength you cannot launch that the signal from that your transmitter. Okay.
Okay,
so
thank you, sir.
Yeah, so to launch that signal, you should have that the low high frequency, or that your wavelength should be that the low.
Okay, thank you, sir.
Thank you.
So I think there is no more raised hand. So here we will try to conclude the session. I take this privilege to extend my gratitude to Professor Kumar Vaibhav sir from IIT Kanpur for it was really a very, very informative and knowledgeable session, sir, really practical oriented. And definitely we, the young academicians, researchers, and our students will definitely be benefited by this session, and will try to expand our horizons in RF and wireless communication domain also. Thank you so much, sir, for joining us here on this platform. Thank you so much, sir.
Thank you, Manisha ji. Thank you.
Okay, so here we have another next session with Dr. Anurag Chauhan, sir. So let me call first Dr. Anurag Chauhan, sir. Are you there? I request the technical team, please make co-host to Dr. Anurag Chauhan so that sir can unmute. Sir, are you getting me?
Yes, ma'am. Ma'am, I'm audible?
Yes, sir. Now you are audible, sir. So,
yes,
very good afternoon to one and all here. Now we have with us Dr. Anurag Chauhan, Assistant Professor from Department of Electrical Engineering, Rajki Engineering College, Banda. Sir will demonstrate electrical machine lab. So firstly, I would like to take privilege to introduce Dr. Anurag Chauhan here. Sir holds Bachelor of Technology degree in Electrical and Electronics Engineering in year 2008 from Dr. APJ Abdul Kalam Technical University, Lucknow. Sir has obtained his MTech degree from IIT Roorkee in year 2010 and PhD in Renewable Energy from IIT Roorkee in 2016. Sir has published 6 papers in international journals and 13 papers in conferences indexed in IEEE, SCI respectively. Sir has organized almost 13 plus workshops, seminars, conferences, short-term courses, FDPs, etc. Sir has delivered number of expert lectures, and he has also published 4 book chapters of Taylor and Francis Spinger. So without taking much time, let us welcome our next speaker, Dr. Anurag Chauhan, sir, from Rajki Engineering College, Banda. Welcome, sir. Over to you, sir. Anurag Chauhan, sir, are you getting me? Sir, you are not connected via audio. Please check your connections. As I can see, Your audio is not connected, sir. Yes, sir. Now please unmute yourself. Anurag sir, please unmute yourself. Am I audible to you, sir?
Am I audible, ma'am?
Yes, sir. Now you are audible.
Hello?
Yes, sir. You are audible now, sir. Please go ahead, sir. You are audible and visible as well, sir.
Hello?
Yes, sir. You are audible. Please.
Yes, ma'am. I think, yes, ma'am. I think there is a, yes, ma'am. Hello, everyone. I am Dr. Anurag Chauhan. I will brief you about electrical machine one lab. All of you are aware of electrical machines lab. Various kinds of.
Sir?
Yes, ma'am.
Would like to interrupt in between, sir. Your voice is not coming clearly. There are some interferences. I think mic problem or something like that, sir. Please check once.
Oh, okay. Hello. Now voice is clear, ma'am?
Bit clear, sir. Not very much, sir.
Okay, I'm not using this microphone then. Now
yes,
my
sir.
voice is clear, ma'am?
Yes, sir. Better,
Okay.
sir.
Okay, fine. Hello, everyone. I am Dr. Anurag Chauhan. Today, I will brief you about the electrical machines one lab. In electrical machine one lab, we have various kinds of experiments, like we have DC generators, we have DC motors, we have transformers. So today we will discuss about the DC generators characteristics, further DC motors experiments, and we will deal with the speed control of the DC motors. So I am sharing the link directly because for demonstration we need VLab portal. So I'm sharing my screen. It's taking a little bit time because of
Sir is starting his lab. Meanwhile, there is an announcement for participants. Participants, we are sharing feedback from attendance link. Here is in chat box and also in your WhatsApp groups. So please fill your feedback from attendance form. I request to our student coordinator, Neetu, please share the link. Sir, I think there is low bandwidth at your end. Anurag sir? I think there are some technical issues. Yes, sir, you are back now. Sir, please unmute yourself. Yes, sir. Yes, sir, you are visible, sir.
Yes, ma'am. Ma'am, is the screen is sharing? Is the screen shared? Is
No,
seen?
not yet.
I'm
Sir.
sharing
Please.
my screen.
No, sir, not visible. Please share again.
Okay. What is seen, ma'am?
Yes, sir. Mic is okay, sir. Now you are
It is
visible.
seen
Please.
now?
Yes, sir.
Okay. So today I am starting with the first experiment of.
Sir, I think you are on low bandwidth. That's why you are disconnected in between.
Yes, ma'am. There are certain issues frequently arising. Now the screen is visible, ma'am.
Yes, the screen is visible, sir.
Now the screen is visible, ma'am.
Yes, sir. It is visible now, sir.
Okay, ma'am. So today we will discuss this first experiment of load characteristics of DC generator. So first, the theory part we will see. In theory part, of course, we will put some load on DC generator, and then we will draw the characteristics between the terminal voltage and the load current. So accordingly, we will have the graph of speed versus load current. The next slide we will see what is the theory behind the experiment.
Sir, I think there are some network issues at your end. So if you want, we can take a break here for 10 minutes or 15 minutes, whatever you want, sir, so that you can resolve your network issue and you can switch over to another network, like using your router or something else. And meanwhile, we will take a break. If you say so, we can do this thing because your connectivity is not very good, sir.
Okay, ma'am. I am connecting with it after 10 minutes, ma'am. Sure, ma'am.
Okay.
Sure.
Okay, please take your time, sir. Okay. So participants.
Yes, ma'am. Yes.
Thank you, sir. So participants, here we will take a short break of 10 minutes. I really apologize for the inconvenience caused to you. And after 10 minutes, we will all come back with this session. Meanwhile, I request to our technical team, please stop the recording on YouTube. Sir, please disconnect yourself and switch on another network.
Yes, ma'am. Yes, ma'am.
Okay, take your time, sir. No issue, sir. Meanwhile, we can take live feedback from participant side also. So if someone want to share something about views or any feedback to make it more beneficial for the students, so please raise your hand. We will try to connect you. Yes, I can see Rajendra is there. Yes, Rajendra, now you are unmute. Please ask your, share your views. We are trying to connect our expert very soon. Meanwhile, all the participants, please fill the feedback form and attendance form.
Ritika Thakur from BTech ECE second year welcome you all. Institute of Engineering and Technology, Ayodhya is one of the best engineering college in India. Under the kind guidance of our respected director and our honorable Vice Chancellor, our college has flourished a lot and will keep on moving till it achieves a great height.
Institute of Engineering and Technology was established in year 2000 by the then Vice Chancellor Professor Girish Chand Saxena, who made it as his brainchild. Now only after 17 years, Professor Manoj Dixit sir is nourishing and nursing this IET as his main institute by appointing full-time engineering domain director in IET. Now let's go around our institute to see the infrastructure and facilities of your own. Under building infrastructure, we have this first building, Visesariya Bhavan, as Institute of Engineering and Technology started. Then we have another building, mechanical building, and that is Meghnath Saha Bhavan, which is having inbuilt Kalpana Chawla Sabhagar for the capacity of 125 students. Along with this, we have boys hostel, Saryu hostel and Locus hostel. For girls, we have Ahilyabai Holkar Chhatravas and Acharya Narendra Dev hostel situated in main university campus. Along with this, we have one international guest house, Sri Gendalal Dikshit Atithi Grah, which is catering to the education of IET. This is a smart classroom equipped with LCD display system. In this classroom, final year students come for presentation of their projects on state-of-art technology available on par with any other engineering college. This lab is research lab and used by final year students as well PG students. This lab is equipped with MATLAB and HFSS software funded by World Bank under TAKIP 3 scheme. This is Internet of Things Lab, Computer Networking Lab, Digital Image Processing Lab. Again, this is funded by World Bank under TAKIP 3 scheme. And in this lab, currently, students are working on IoT-based pollution meter and IoT-based smart camera. This is our Intellectual Property Facilitation Center. Now we have started final year engineering projects, documentation and their innovations for intellectual property rights. This cell is first of its kind in Uttar Pradesh engineering colleges, which is motivating the students to go for innovations. This is lecture hall of IIT. Like this, we have 34 lecture rooms and nearly 80 faculties are catering to the education of all IIT students. Now with this, we are having capacity of taking admissions more than 500 students and thus needing the technical power need of our Hindi heartland. This is skill development and languages lab of IIT. In this, students are given facility to improve their English language and also enhance their technical skill so that they become more employable as per the need of industry. This is first year physics lab in which students are able to perform physics experiments based on mechanical, optical and electrical, ranging from Kelly-Foster bridge to sonometer to optical fiber lab and torsion meter. This is mechanical engineering workshop practice lab for first year students. This lab is comprising of all lathe machines, hexa machines, cutters, shapers and milling machines.
It's been so many years. I still remember the year 2000 when this Institute of Engineering and Technology was established. And I also remember the first batch of IIT. Your faces are still so fresh in my mind. Now you all are grown up, well established in your fields. But for me, you all will be my loving students forever. To recall all those memories, we have decided to conduct an alumni meet in your city. Our first alumni meet was organized on 14th February 2019, but due to distance, it was not a successful one. So we have decided to conduct an alumni meet in your city. And I am very excited to meet you all in this alumni meet.
Yes, I am very happy that I have been teaching for almost 15 years. I joined at a time when good resources were not available. Under the direction of the Honorable Vice Chancellor Professor Manoj Dixit and Director Professor Ramapati Misra, new work done in IT, such as organize different workshop and seminar, faculty development program, national and international conference on different technologies, training and placement program. Students are placed in different government and private sector on repeated posts to develop new infrastructure for IT, due to which IT no longer working with any NIIT. In such situation, our alumni meet with new student and new energy will be communicated.
In national level techno exhibition, we won first prize and the cash of 1 lakh rupees. Me and my team did a lot of hard work in this project along with the support of our VC sir, director sir and TAKIP coordinator.
Other than those facilities, we have advanced library equipped with the facility of Wi-Fi to help students in their studies. Workshops, seminars and industrial visits are conducted on a regular basis to help improve our knowledge and give us a practical outlook of life. Art of Living is conducted every day to relieve us from the pressures of life. Sport activities are conducted regularly to keep us fit and healthy.
Our college has been converted into a clean campus, green campus,
The entry of only electronic vehicles is allowed. No pollution or environmental hazards are allowed in this campus. The students are not allowed to smoke or cause any pollution in this campus. And we have also planted a lot of trees under the 9 crore program of Chief Minister, plantation of trees.
This is one small step into the future of Engineering College at Ayodhya. We always knew that the alumni of this institution are spread far and wide all around the globe, but there was no platform to put them all together to make their efforts count towards their own alma mater. And today, with this organization of this function, I think we have covered a mile with a small step, baby step. But we look forward to many more such events in future, in many more cities, wherever we are, and we must be able to achieve the target of what we call as learn, earn, and return. I'm thankful to all those who have made their efforts to make this event successful. Also thankful to the institution which has allowed us to host this function here. It's wonderful to see past students coming here, having a good time with us, and I look forward to their contribution, a meaningful contribution, not necessarily monetary contribution, but definitely meaningful contribution for networking with the students of the present and also giving them all their advices and mentoring whenever and wherever they need it. I think we will continue to meet, organize such events, and look forward to all of you coming together in Ayodhya at any opportune time. We will be more than happy to welcome you all in Ayodhya.
So friends, I leave on to you to decide and rate our IIT Ayodhya. We all welcome your advice to fulfill our thirst of improvement, because where there is a skill, there is a way. Thank you. Jai Hind.
Thank you so much, Ramesh sir, for such a nice video of our college you have shown. Meanwhile, once our speaker got connected again. Now, once again, welcome to Anurag sir. And I think sir has resolved his network issues. So we will continue and proceed over to session. Welcome you, sir.
Yes, sir. Thank you, ma'am. Thank you. Sorry for the inconvenience, ma'am.
Okay, sir.
Now, yes, ma'am. Now I am sharing my screen. I think it is visible to all of you.
Sir. Yes, sir. Now it is visible, sir.
Yes, ma'am. So now I'm starting with my first experiment. This is the load characteristics of a DC generator. So basically, a DC generator characteristics is required to obtain the behavior, how it behaves under different operating conditions. So it is basically just gives the speed variation. Suppose I have the experiment of, I have the simulator of a DC shunt generator on my screen. You can see I have certain expression. You can, you have to connect all the connections before getting the results. So you have MCB over here. You have the starter. The starter is required for DC motor because to limit the value of current at starting. And we have the ammeter and voltmeter, and for the measurement of voltage and current. So first of all, we have the connection. We have the circuit diagram. We have already studied in our theory subjects. And so accordingly, we have to connect the circuit diagram. So first of all, where we have MCB. So according to the procedure, we have the procedure in our VLab. So in VLab, accordingly, the procedure, in the procedure, the connection diagram is given and the connection points is assigned. So accordingly, you have to connect. Suppose this is the line This is the field connection. This is the armature connection. And this is the L1 and L2. These are the terminals of the loads. We have the different kinds of lamp over here. And in order to run our DC generator, we need some prime mover. And here we are considering DC motor as a prime mover, which rotates the shaft of DC generator. And generator converts mechanical energy into electrical energy. And this energy is used in the lamp, which is over here. We are using the bulb for as a load. We can change the load. We will check the speed variation as well. So first connection, which is given in the procedure, you can see the procedure, and you can go. These are also given in the instruction set. So procedure is also given in the instruction. Accordingly, you have to connect 1 by 1 point. No change is permissible here. So accordingly, you have to connect. Otherwise, it will show the error. Like other speakers, renowned speakers have already told that it will show error, and you have to connect whatever the procedure is. So like first in the procedure, the first step is given. Positive terminal of MCB is connected to positive terminal of ammeter, meter 1. So we have two ammeter. This is ammeter 1. So positive terminal of MCB goes to positive terminal of ammeter. This is A meter 1. Second step is positive terminal of MCB. This one goes to the positive terminal of V meter. So this is like this. Third step of the procedure told negative terminal of MCB, which is this one, is connected to negative terminal of voltmeter 1. So we have voltmeter 1. This is the voltmeter 1. So we have to connect the negative terminal of our MCB to negative terminal of voltmeter 1. Further, at the fourth step of our procedure, the negative terminal of MCB, which is this one, should be connected to the A2 of motor. But where is A2? A2 is here. A2 motor, this is the prime mover, which acts as a prime mover for DC generator. So we have A2. So we will give some supply. So negative terminal of MCB goes to A2. So A2 is this one. So you can connect. Further, at the fifth step, which is also given in the instruction, or is also given in the procedure, A2 is connected to F2. So you should know where is A2. A2 is here, and A2 is connected to F2. So F2 is here. So here the terminal F2 is wrongly said because there is no F2, there is Z2. So you can use the terminals F1 and F2 as well, because these are the terminals. You can see that. So A2 is connected to F2. Further, the line terminal is connected to negative terminal of the ammeter A1. So you can connect right here. And F is connected to A1. So here is a field terminal and is connected to Z1 from this connection. And the A, this is the field connection, this is the armature connection, this is the line, this is field, and this is armature. So armature connection is connected to A1. So obviously it goes to the A1, that is the terminal of armature of DC generator. L2, which is L2 is connected to A2. So L2, you have the L2, this is the terminal of the load, and it is connected to A2. So A2 is here. And further, A2 of generator is connected to F2 of generator. So here F1 and Z2, they have wrongly placed, but it is the same meaning that F2 and Z2 are the field terminals. So you can connect A2 of generator to the F2 of generator. Then F2 of generator is connected to negative terminal. Meaning this connection should be connected to negative terminal of voltmeter 2. So we have the voltmeter 2 over here, V meter 2. So you can connect the negative terminal. So you can connect from F2 to negative terminal. Then at the 12th step, negative terminal of A, negative terminal of ammeter 2 is connected to positive terminal of voltmeter 2 is connected. Then L1 means load type. This is L1, positive terminal of the load, and it should be connected to positive terminal of voltmeter 2. So you have positive terminal of voltmeter to right here. So you can connect this connection to here. Further, at the next step, this is the second last step. 2 steps are remaining. So it says that positive terminal of A, ammeter 2. So we have the positive terminal of ammeter 2. It should be connected to A1 of generator. So this is A1. So you can connect this here. And further, positive terminal of ammeter A, this is this one. It should be connected to Z1 of generator. So you can connect this. So this is the connection diagram based upon the procedure which is given in the manual. And then after the proper connection, you can check whether this connection is right or wrong. If this connection is wrong, then it will show warning and we have to again reconnect. So you can check button. So the warning came and it says that it is the correct connection based on the procedure which is given in the, and the motor starts. As you can see, the motor has been started. You can click on the MCB switch and you can see the motor has been started. Means DC motor is the input and DC generator has been started because it's taking the input from the prime mover. So after this connection, you have to plot a diagram between the terminal voltage and the load current. So this is the external characteristics. If you plot internal characteristics, it means the DC generated voltage versus load current. And if you want to plot external characteristics, it means the terminal voltage versus load current. So both the, this is the way by which we can measure the load current and this is the voltmeter by which we can get the voltage across the load. So at no load, obviously there is a more voltage which is equals to generated voltage after deduction of armature reaction. However, as soon as we increase the bulb, suppose we are taking the first number of bulbs, you can get the reading, right? So this is the ammeter for this one motor and this is the voltage for this motor. However, for DC generator, the value of current is less because only the one bulb is connected and the voltage value, the terminal voltage value is very high. As soon as you increase the value, the voltage will decrease because of armature resistance drop and armature reaction drop, and the value of current will increasing. So we will take this reading, we will save this result. We have same result that 220 volt is, we have the rated voltage. Again, we increase the loads like from 1 to 2. The value of current is increasing, the value of voltage is decreasing. You can add this result in your table, right? So the value of current is double, almost double, and the voltage value is decreased from 220 to 212 volt. Similarly, you can take 5 results and you can add all the results. As you are increasing the load, the value of current is increasing and the terminal voltage is decreasing because of the armature reaction drop and the resistance, armature resistance drop and armature reaction drop. Again, you have increased load, you have some values, you are saving this in table. So at least 5 reading you should take for plotting some graph. So you can continuously see that the value of the load current is increasing and the value of terminal voltage is decreasing. That is what the characteristics. Characteristics means the behavior of this machine under different loading conditions. So you can plot this. You can plot some graph. Minimum 6 reading is required. The accumulator is saying 6 readings. So again, you can check one more. 5 you have already taken. And you can add this result in your observation table and you can plot now. Yes, it is visible on your screen. All of you, all the students can see how the voltage is varying as the load current is increasing. So this is the characteristics. So from 220 to it is around 195 from the current varying from 1 ampere to 7 amperes. So you can see the variation. Accordingly, you can calculate the voltage regulation as well. Voltage regulation says that the variation from no load to full load, and you can calculate the voltage regulation for DC generator as well. So any student who has some confusion, they can write me back. in the comment box. So accordingly, you can complete the experiment of the other section also.
One
Hello?
question is there, as I can see in chat box, sir. The question is, can we observe starting current?
Yes, ma'am.
There is a question, sir, in chat box, as I can see. Question is,
yes.
Can we observe starting current?
Yes, ma'am. Starting current, you can see because now side is disconnected, but this other things. Actually, when no load is connected, so of course we have no load. So obviously the load current is 0. So we have the terminal voltage 220 volt is equals to rated voltage. So and of course when no load is there, so starting current you can assume 0. The starting current will be 0 if we have no load. As soon as we increasing the load 1 lamp to 2 lamp, 3 lamps, the increasing current will be achieved. It will be increasing 1 ampere, 2 ampere for the 3 amperes, 4 amperes. Yes, ma'am. Any more questions, ma'am, on this segment?
Yes, sir. Thank you, sir. There is another question from Surya Narayan Ji in chat box. Wanted to know whether the high starting current of motor can be seen or not.
High starting current is of course we have already we have the simulator in our section. In simulator you can see we are using starter. So starter basically reduces the current. The starting current, of course the starting current will be very high. So we will limit this current using this starter that already modeled through programming in our simulator. So of course in this case the starting current will be in our control. It will be as minimum as possible. Ideally it should be 0 ampere, but it should be take some current. So with the help of starter we have minimized the current. So there will be no such case of high starting current, ma'am.
Okay, thank you, sir. I think Surya Narayan sir has got his answer. So no more questions is there in chat box? Yes, he is replying. Thank you. So please proceed over the session now, sir. You can continue now, sir.
So I can go to second lab. Is the time permit, ma'am?
Yes, sir. Time is all yours, sir. Please go ahead.
Okay, thank you, ma'am. So we have the second experiments of Ward-Leonard method. So field resistance control and armature resistance control are quite easy. You can also do your own. So I'm directly went to the third speed of control, which is armature voltage control, which is Ward-Leonard method. Other two methods are armature resistance control and field resistance control method. They are basically, we have some resistance and we put in the series with armature circuit, or we put some resistance in the field circuit in order to limit the speed. We have the third method, which is very important and it can be asked any exam or interview. What is Ward-Leonard method? What is Ward-Leonard method? This is basically armature voltage method. As you can see, the speed is basically depends on V minus IRA upon K5. This is a basic rule. Any book you can use or refer any book or standard book. So there is certain expression like if we have motors, so V equals to EB plus IRA, and we have EB equals to V minus IRA, and N equals to V minus IRA upon K5. So we have armature resistance control, we have field resistance control, and then something is V. So V is, that is armature voltage control. If we anyhow we can control the armature voltage, so we can reduce or increase the speed. So both advantage we can get. So that's why I am using this screen on the simulated screen. rest of the procedure you have already studied in the books. So first of all, there are certain things we need. We need some like induction motor, which is a prime mover for the DC generator. This is called as the motor generator set. This will basically, this is a DC motor to whom we am applying the armature voltage control. So induction motor and DC generator basically provides the input or electricity to the DC motor. So we will increase or decrease the voltage to this DC motor so that we can increase the speed or decrease the speed as well. So connection you already have in your instruction, you can read it, and also it is given in the procedure of this simulator. You can see in the VLab portal. So I'm just connecting one by one, which is given in the procedure. Don't connect any other procedure, because it may show the wrong connection, because the coding is done accordingly as per the procedure. So we have the word EONOD method with us. So I'm doing the connection as per the procedure which is given in the simulator, because the programming has been made accordingly for the simulator. So the first step is given connect point A1. We have connect A1. This is the three-phase supply which is required for your induction motor. This is DC supply which is required for which may be required for other loads which is in the circuit. So we are connecting which is given in the procedure. So it is given the first step. There is a 6-step or A1 or A2. So we have the connections, numerous connection for this. We are connecting one by one. So we have three-phase supply. So we will connect. It is required for three-phase motor. So accordingly we connect to the motor. All right. So this is the auto transformer, three-phase supply. We are giving the supply through auto transformer, because slowly we give the voltage to the induction motor. This is your three-phase induction motor. And further, this connection after D1 to, you can connect E1 to E2. You can connect F1 to, F2, and you connect G1 to G2. Because this is a three-phase supply, you have connected to the auto transformer, because of slowly you are applying the voltage to the three-phase induction motor. And further, A1, A2, B1, B2, C1, C2 has been done, D1 to D2. So we have DC supply. This is connected to the D2. E1 is connected to E2, already done. F1 is connected to F2, done. G1 is connected to G2, done. H1 is connected to S2. So where is H1? H1 is starter. So H1 is connected to S2. All right. Then H1 to I1. H1 to I1. So we have I1. Because this is the field terminal. You know that in starter we have three terminals: line, this is field, and this is armature. So field connection has been done. This is the DC generator you have. This is the DC motor. This is the DC generator, and this is the DC motor to whom we are applying our Leonard method. So H1 to S2 is done, and H1 to I1 is done. But we are connecting rheostat. So the second terminal J1. You have to find J1. J1 is here. This is the armature. It will go to the armature. This is J2, and then J1 to I2. J1 to I2, it is done. And then K1 to K2. You have the K1. K1 is, you have to find where is K1. This is the K1, and you have to connect it through the K2. And then K1 to L1. This is K1 and L1 is here. This is the negative terminal of the armature, which is connected. And then L1 to L2. We have L1 and we have L2. L1 to L2. L1 is here, and then L2 you can connect. This is L2. So you can connect L1 to L2, and then L2 is connected to M1. So this is, and this is L2 is connected to M1. So you can connect L2 to M1, and K1 is connected to M1. So where is K1? K1 is here, and you can connect K1 to M1. And then further I2 is connected to M2. So here is I2, and here is M2. So you can connect I2 to M2. M1 to N1. So we have M1. M1 is here, and M1 is connected to N1. So you can connect to N1. And on the last step of this connection is N2 to O1. And we have N2 to O1. So N2 is here and O1 is here. So this is the procedure or connection which is shown for this simulator. However, we can see this electrical. We have our own connection. Like we have the negative terminal for the DC. We have the positive terminal of the line for the DC. So there are various connections by which you have the line phase, you have the ground phase. But the problem is for the simulator that whatever is given in the procedure, you have to follow that one. Otherwise, it will show the error, because accordingly the simulator has been designed, which has been given in the procedure. So it is our boundness to use that one. You can build your own simulator if you are interested in that. The thing, but you have to connect the type component as per the procedure which is given. Again, you can click on the check. It is saying that it is a correct connection. Proceed to take reading. I have done several other possible combination which are depends on the permutation and combination, but it's showing the error because our the connection is okay as per the diagram. We have motor generator set and we have the DC motor. Because the simulator is accordingly designed, so you have to use the connection as per the procedure which is given. So as it is saying, it is a connect diagram. So you can switch on the MCB. This is the MCB. It will on only when the connection is okay. It is saying that the connection is okay, and it is saying that double click on the auto transformer in order to start the motor. So you can double click. So slowly it will increase the voltage, because slowly with increasing order you can apply the voltage to the 3-phase induction motor. As it is a self-starting motor, it will start. And this is the armature voltage control. The DC motor is getting the torque from the DC generator. It is getting the electrical supply. That the connection is armature connection is connected across the armature terminal. So you can connect. It is getting the supply from the DC generator. Now you can increase the you can change the generated voltage of the DC terminals through this diagram. However, we have to take the reading from the beginning. So I'm just go back. I am saving this value. It is showing that the speed is very high, 1499 RPM. The voltage is high, and again I am reducing the voltage through the resistance across the field resistance of the we are reducing field current, so obviously field flux is reducing, and the generated voltage of the separately excited DC generator is decreasing. So if we decreasing the voltage of course V minus IRA upon K5, if you decreasing the value of V, so obviously the speed will go down. So speed will go down. You have to take at least 6 readings at you have seen in the earlier experiment. So you can increase the voltage as well. You can decrease the value of voltage, and you can save the value for the 3 more readings you have to take. Again, you have to increase the value of resistance and decrease the value of field flux. the value of speed is continuously decreasing because the voltage across armature is continuously decreasing because of this field resistance of generator. So we have taken 5 reading, 1 more reading is required. As a simulator is designed, the value of speed is go down. So accordingly, graph can be plotted, the value of speed versus voltage. You can see at the bottom of the simulator, the graph has been plotted. You can see the value of the voltage is decreasing across armature circuit. The value of speed is decreasing. Minimum 6 points you have to take for this simulator. So this is the armature voltage control through which we can decrease the value of speed below the base speed. Suppose the base speed is 1200 RPM, so you can decrease the value of speed at the rated speed. We are not going the above speed because we are increasing the field flux. That something condition is achieved like field saturation. So we are not increase the speed from the base speed, so we are reducing it. We can increase the speed, but the condition is that the field must not be saturated. If it is saturated, then obviously we can decrease the speed. We cannot increase the speed. Yes, ma'am. So this experiment is completed. If participants have questions, then they can ask.
Okay,
Hello.
sir. Yes, sir. One question, as I can see, floating is in chat box, sir.
Yes,
Why
ma'am.
the efficiency of Ward-Leonard speed control method is less in spite there is absence of external resistance in this method? Sir, you can also read in chat box if you can see.
Okay. Yes, ma'am, I can see.
Yes, sir. Participant, you may directly interact also. Please avail the facility of raise hand. So you can ask your question directly also. Sir, you are able to see the chat box?
Yes, ma'am, I'm just seeing, ma'am.
Yes, okay, sir. Sir, should I read out the questions? Anurag, sir?
Ma'am, my voice is audible, ma'am?
Yes, sir. Sir, let me read out the question. Okay.
Ma'am, actually the chat box is not opening. So
Okay, okay. I am reading the question, sir, one by one. Okay, sir. So first question is why shunt generator load characteristics turns back when overloaded?
Yes, ma'am. Please repeat.
Why shunt generator load characteristics turns back when overloaded?
DC shunt generator. Okay, ma'am. Okay. Ma'am, the DC shunt generator is basically when we are loaded. Suppose we have no load. Obviously, we have the terminal voltage is equals to our generated voltage. As soon as we apply the load, the terminal voltage is reducing due to armature reaction, and the voltage resistance drop due to armature resistance. So these are the two factors by which we have the less voltage as compared to the generated voltage. We may have the overload voltage as the question is asking. So it is possible only for over compounded generators. So DC generator, it is not possible. However, we can use other generators like DC compound generators. We have over compounded generators. So we may have the over voltage like the question is asking. But in case of DC generator, it is not possible. No?
Okay. Sir, another question is there. Repeat the add value. Repeat the add value. Yes, sir. This question is in chat box, sir. Actually, I'm not from electrical background.
No problem. No problem. Actually, the question is asking for simulator, which has been developed for the machines. So, like add values means minimum six readings you have to take for observation table as a simulator has been designed. We can draw it for 2 points or 3 points at least. It is required for the graph characteristics. But we need 6 add values, 6 readings we have to take for the proper characteristics of the DC motors. So we have to take at least 6 reading add values for the observation table as the simulator is designed for the 6 readings. Yes, ma'am.
Okay, sir, another question is, I would like to request Vipin Patel to please unmute yourself and please directly interact to our speaker. Vipin Patel, you can unmute yourself, sir. Yes,
Hello.
sir. Please continue, sir.
Good afternoon, sir.
Yes, sir. Please continue, sir.
After how much percentage of loading shunt machine gets breakdown? Hello.
Yes, sir. Yes, sir. You are listening. Yes, yes. Please repeat.
Yes, sir. After the percentage of loading, after that shunt machine gets breakdown occur.
Percentage loading, it is vary from. Yes. Can I respond?
Hello.
Yes, sir. Yes, sir. Bilkul.
Yes, yes. So, like breakdown is the thing which varies from rating to rating. Suppose we have small rating DC generators and we have large rating DC generators. So, up to 50% loading we can give without any breakdown for the small machines. However, for larger machines, the breakdown torque can be double. So, it is not fixed as such. So, from rating, it depends on the rating of the DC generator. You can move up to 50%.
Okay, sir. Vipin, sir.
Okay, sir. Thank you. Thank you very much.
Thanks, sir, for asking question. Another question, sir, is in chat box. That is, in Watt-Leonard control of DC motor, how the lower limit of speed is imposed?
On the lower speed. Okay, so lower speed is basically as soon as we decrease the voltage, the value of speed obviously go down. We decreasing the voltage, the value of speed is go down for the DC shunt generator. For DC shunt motor we are taking. So how much DC? So there is a critical speed phenomena. Critical speed by which we can, this is the critical speed is decided based upon the critical resistance by which we have started the motor. So there is a critical speed value. So it is different from machine to machine. Yes, of course, we have, suppose we have critical speed of 200 RPM. So we cannot go beyond less than the 200 RPM. So this is the word is critical speed. You can go refer the books, you can refer the VLabs. So below critical speed, we can not go because it will, the characteristics will be know how it will be not behave, like characteristics will be drastically changed. So critical speed, up to the critical speed, we can reduce the speed. Yes, ma'am.
Okay, thank you so much, sir, for clearing the things and explaining in good way. As I can see, there is a raised hand from a student, Vishal Sharma. I am trying to unmute Vishal. Please ask your question.
Sir, why the efficiency of Leonard
Vishal, please continue.
why the efficiency of Ward-Leonard speed control method is less in spite of absence of external resistance?
Efficiency you are talking, Vishal?
Sir, Ward-Leonard motor.
So efficiency is very low because we have a lot of conversion, because we have three-phase AC supply is given to this AC three-phase induction motor. Then the induction motor is acting as a prime mover for the DC generator. So there is a electrical energy to mechanical energy conversion, and then again the output of DC generator act as a input for DC motor. So again we have a conversion of mechanical energy to electrical energy. So we have 2 or 3 conversions. Suppose 1 conversion, 2 conversion, 3 conversion. So in 3 conversion, obviously there are certain kind of losses are there. Like if mechanical losses you are talking about, so we have frictional loss, rotational losses, bearing losses. And if we are talking about electrical losses, we have various kinds of losses such as ohmic losses, eddy current loss, iron loss. So these are the factors by which we have very low efficiency for Ward-Leonard method. Although it is very effective to test a machine, to calculate the efficiency, to have very large variation in the speed, but due to 3 conversion, we have very low efficiency, Vishal. I think I am clear to you, Vishal. Is it okay? Okay, thank you. Thank you, sir.
Okay, thank you, sir, for answering. Another raised hand is Rohit Vishwakarma. I'm unmuting you. Please ask your question.
Hello, good afternoon, sir.
Good afternoon, Rohit.
सर ये डीसी शंट जनरेटर जो होता है सर
जी
हेलो सर
हाँ मैं सुन पा रहा हूँ आपको बोलिए बोलिए
सर जो डीसी शंट जनरेटर होता है सर वो सेल्फ एक्साइटेड पे फेल क्यों हो जाता है सब सेल्फ एक्साइटेड कंडीशन होती है तो वहां पे फेल हो जाता है सर इसका रीजन क्या है
कि सेल्फ एक्साइटेड एक वर्ड है कि हम बोलते हैं कि सेपरेटली एक्साइटेड होते हैं
सर क्वेश्चन ये है अंडर व्हाट कंडीशन डज द डीसी शंट जनरेटर फेल टू सेल्फ एक्साइटेड
अंडर व्हिच कंडीशन डीसी जनरेटर मोटर है सेल्फ एक्साइटेड मतलब उसकी कंडीशन सेल्फ एक्साइट नहीं हो पाता है ना
यस सर फेल टू सेल्फ एक्साइटेड तो सर क्यों होता है
देखिए दो ही रीजन है मैंने बात की थी अभी सेल्फ एक्साइटेशन की सेपरेटली होते हैं एक सेल्फ एक्साइटेड जनरेटर दो जनरेटर है हमारे पास सेल्फ एक्साइटेड में डीसी सीरीज है डीसी शंट है चाहे कंपाउंड जनरेटर्स आप ले लीजिए शॉर्ट शंट लॉन्ग शंट है ना तो एक्साइटेशन की जहां तक बात है क्रिटिकल रेजिस्टेंस एक वर्ड है और दूसरा है क्रिटिकल स्पीड तो अगर हम किसी कारण से क्रिटिकल स्पीड मेंटेन नहीं कर पा रहे हैं या फिर क्रिटिकल रेजिस्टेंस जो हम दे रहे हैं या फिर जैसे कि ब्रेकडाउन की बात की अगर हम ऐसा लोड लगा दे रहे हैं जो कि बियरेबल नहीं है मान लीजिए 50% लोड है 50% ओवरलोडेड आप उससे ज्यादा ले जा रहे हैं तो दीज आर द 3 फैक्टर्स तो ये 3 कारण हो सकते हैं जैसे कि आप कह रहे हैं कि डीसी शंट जनरेटर सेल्फ एक्साइटेड मोड नहीं हो पाता तो ये 3 रीजन हो सकते हैं क्रिटिकल रेजिस्टेंस हम मेंटेन ना करें क्रिटिकल स्पीड हम मेंटेन ना करें और तीसरा है कि हम ओवरलोड उस पे अप्लाई कर दें तो देयर आर 3 कंडीशंस रोहित
यस यस सर
तो क्या आप आंसर से संतुष्ट हैं तो देयर आर 3 फैक्टर्स
जी सर थैंक यू सर
कोई भी फैक्टर जरूरी नहीं है कि मैं तीनों भी हो सकते हैं एक भी हो सकता है लेकिन तीनों में से अगर एक भी हो जाएगा तो वो डीसी जनरेटर आपका सेल्फ एक्साइटेड नहीं रहेगा
Okay, so thank you so much, sir, for answering questions. If Any other question is from participant side? So please be quick and ask your queries. Please avail the facility of raise hand, or you can write in chat box also. So I think, sir, there is no more questions. So at this note, we are wrapping this session. I would like to extend my gratitude to Dr. Anurag Chauhan, sir, from REC Banda. Thank you so much, sir, for sparing time with us and showing live demonstration of lab. Sir, one more question if you can take. Is machine ratings are mentioned? Is machine ratings are mentioned? Question sir ये है chat box में sir. क्या machine?
Yes ma'am. Yes ma'am. Yes, I have heard ma'am. So machine ratings are essential. Like we are talking about today, we have discussed about at Machines One Lab. This is basically deals with DC motors and transformers. So DC machines are basically rated in kilowatt. Of course, it is the basic requirement. Because DC motors, we have various kinds of losses, copper losses, mechanical losses, all are rated in kilowatts. So obviously, this is the basic factors. This is kilowatt is the rating, voltage and ampere. These are the three basic ratings which are essential for a DC motor. So rating is very important parameter.
Thank you so much, sir, once again. Now we are wrapping this session and extending gratitude to Dr. Anurag Chauhan, sir, for sparing time with us and giving live demonstration of electrical machine lab. So thank you, sir, for joining us.
Thank you, ma'am. Thank you. Thank you so much.
Participant, here I want to announce that we have already shared a feedback attendance link in chat box as well as in WhatsApp group. So please be quick to fill your response. And we are ending this day now, and we will rejoin again tomorrow at sharp 10:30. So thank you all. Thank you, participant. Thank you all the members. And thank you, Dr. Anurag Chauhan, sir.
Thank you, ma'am. Thank you. Thank you.
I would request to our technical team, so please end the session now.